Right, okay, let's have a look at some more difficult ideas of moments. So this is some of the ideas that you might get wrong when you're tackling some moments. So the first one is understanding that there's nothing wrong with a force as long as it is at right angles to the pivot. So say we've got two forces, one going up there and one going across there. This could be a rotary door or anything like that. It could be a bike handle. I've seen all kinds of examples of things where they use moments on them. So yeah, we've got a push upwards like that, and we'll say that's 800 newtons at 1.5 meters, and then we've got a push of 1,000 newtons, and we need to know the distance. So what I'm going to do here is I'm going to look at this situation. You might think, oh, well, they don't look like they're at right angles because that one's not at right angles to that. Well, it is, but the issue is here is that you get a bit confuzzled at the fact that it's different to what you normally expected. So actually, in this case, we need to look at the line of action from the pivot to where the line of the force is, and we can see that that acts at a right angle. Same for this one, acts at a right angle. So no issues there. You can do exactly the same as you did before. Clockwise moment, anti-clockwise moment. So we've got 1,000 times some unknown is going to be equal to 800 times 1.5. So we can rearrange that to 800 times 1.5 divided by 1,000. 1.2 meters. Okay, so in this situation there's no difference. Try not to get confused by the fact that it is not in a regular arrangement. You can have them anywhere. The force could be acting over here at a right angle, and it wouldn't make any difference. It wouldn't make any difference whatsoever to the fact if that 1,000 newtons was there as opposed to there, that distance would still be 1.5 meters. Okay, so that's a nice thing for you to just to bear in mind. Same thing if it was down here. So if you had a line of action from down there, so there's 1,000 newtons, as long as it's at right angles to the pivot, then we have definitely got a distance of 1.5 meters. Sorry, 1.2 meters, apologies. So that would be 1.2 as well. So it wouldn't matter where that 1,000 was, it wouldn't make any difference. Just bear that in mind, it can be anywhere. As long as it's at right angles. So what happens when it's not at right angles then? So I'll try and give you a simple version as I can. So we've got a beam, pivot, box on the beam, being held up by a wire, 2,000 newtons, sounds good, 30 degrees, that's, what do we do there, it's going to get in the way, distance of 7.5 meters for that one, and a distance of 10 meters for that one. So the question is, how do I find my missing weight or the weight of my box? So we've got our pivots, we've got potentially an anti-clockwise moment, and we would have our clockwise moment as well. Okay, so where do I go from here? Well, unfortunately I can't just do what I normally did. I can't just go, okay, 10 times 2,000 divided by 7.5, it won't work, that's not right, that won't work. What I need to find out is I need to find what the moment is here, that when it is at a right angle. There's two ways of looking at this, two ways. You can either draw a new line to where the force would be at a right angle and work out that distance to plumb into your force times distance calculation, or you can work out the force, the vector of that force that is at right angles to the pivot. So there's two ways. So there's way number one, way number 2. I'm going to show you both ways of doing it. So way number 1, we're looking to find the distance to that 2,000 newtons that is at right angles. Well, what have we been given? We've been given a 30-degree angle. We know that this distance is 10 meters. So we can say that this is a hypotenuse. This is an opposite. So yeah, we're going to use sine theta equals opposite over hypotenuse. So sine theta times the hypotenuse equals the opposite, which is what this is in this case. So sine of 30 degrees times by 10, and we work that out on our calculator. 0.5 times by 10. It's 5. So that's 5 meters. So that's telling us that that distance there is 5 meters to where the force would be 2,000. So we can work out our moment here as the force times distance 2,000 times 5 is going to equal 10,000. Meters. Way number 2. Okay, so this one is the one I use more often than not because I like doing the vector resolution on this to understand the forces. And often this is the way they want you to do it, but if you can do it both ways, brilliant, that's fine. So this time, we're not working out the distance, we're going with the distance, but we're going to work out what the force is at right angles to the pivot here. So over here we worked out the distance to that force as a right angle. Now we're working out the new force at a right angle using this distance. So what we're going to do is we're going to make up a nice little triangle out of this, and we can see that because that's 30, that must be 60 because it's a right angled triangle. So we've got adjacent, we've got hypotenuse there. So this time we're doing the calculation not with distances, we're doing it with the forces. So we're going to be using cos theta equals adjacent over hypotenuse. So we'll go with cos theta times our hypotenuse equals the adjacent, which in this case, cos 60 times by 10. Sorry, no, 10, 2,000 equals the adjacent. So in this case, we'll work that out on a calculator. It's 10,000. Excuse me. So as you can see there, I get the same moment whichever way I do it. Okay, I do it way number 1, I get the same moment. Way number 2, I get the same moment again. Sorry, I didn't times that by 10. Sorry, that gave us 1,000. I was sneezing at the time. That gave us 1,000, and then we times that by 10. So 1,000 times by 10, which is the new force. Force upward there is 1,000. 10 meters. The distance equals 10,000 Newton meters. So it's the same calculation. You get the same overall value. So working out the final result is just a matter of course, really. We just need to just plumb in the numbers. So either which way we do it, we know that the anti-clockwise moment must equal a clockwise moment, so that means that 10,000 must equal to our unknown times by 7.5. So apologies, 10,000 divided by 7.5. 10,000 divided by 7.5. If I could see where the decimal point was. So 1,333 newtons there, so that's 10,000 divided by 7.5. Whether you did it way number one to work out the distance, or whether you would want to do it way number two to work out the force, it doesn't matter. You still have to use trigonometry in both cases, okay, when you've been given an angle. So watch out for angles on moment questions. They're just a way of them extending the question to make it a little bit more difficult and challenging, and we'll have a go at plenty of those in class.